Welcome back to Stewart Science. Today we're talking about how to make a force diagram for an object whose velocity is changing. So how do we draw a diagram that represents the forces on something that's speeding up or slowing down? And we've talked about it before, but I want to reiterate, just because an object is moving doesn't mean that the forces aren't balanced. If an object has constant velocity, that means we need to draw the forces the same strength side to side and up and down. If something is not speeding up or slowing down, it has equal forces. So I want to talk specifically about something that's gaining or losing speed, because whatever way the object's velocity is changing, that's the way we need to draw our longest arrow. So here's a few examples, just for a recap's sake. Let's say our car has constant velocity. How would we draw a force diagram for that thing? So always start with a dot, and then you draw an arrow for every force that acts on this object. So start with a downward arrow for the force of gravity. You might like calling that one weight. It's the same thing. I don't care either way. And then an equally strong arrow, Fn, for the normal force, because this car is on a surface. So now I need to think side to side. So if we have an arrow this way, what makes the car go that way? Well, it's the engine. F, engine. Now, the last question we need to ask is, how big should we make this arrow that goes the other way? Because if we make that arrow the same size, we're saying that the forces are balanced. If we make it smaller, we're saying that the engine is stronger, and we make it longer, we're saying that whatever force that is the stronger force. So since this object has constant velocity, we should make it the same length as the other arrow. That's the engine. So we'll call this F drag. That's our word for air friction. And so since this car has a constant velocity, since you see those magic words, constant V, that means all the arrows should be drawn the same length. So the question to ask is, how does this change if our car, instead of being at a constant velocity, is gaining speed? And the answer is that the arrow this way is longer now than the other arrow because it's gaining speed that way. So if we're going back to our force diagram, we have the same forces, force gravity, normal force. Those should be equal. Forgive my bad art if they're not. And then the arrow to the right here, the engine arrow, should be longer than the F drag arrow. The engine's force is bigger than the drag force because it's gaining speed this way. Now let's talk about another confusing kind of example, which is slowing down. Because this car is still going this way, but its speed is going to be changing that way. So go back to our force diagram, draw our same arrows that we always have, which is F gravity, and normal force. Those are still there. But now we have a shorter arrow for engine, and a longer arrow for drag. Because in this example, even though we're moving to the right, our speed is changing to the left. The overall effect is that we're losing our positive velocity, which means that our net force is that way. So here's an example that's just up and down. If we have a rocket that's blasting off, we have two forces. Gravity, as always, and then this upward arrow needs to be longer than the downward arrow. We call that thrust. because it's gaining speed in an upward direction. Now, after the engine cuts out, that rocket will keep going upward until gravity slows it all the way down. So on its way up still with engine cut, it's still moving upward, but its velocity is changing in a downward direction. And so our force diagram will look F gravity, still downward unless you're out of the Earth's gravity field, and then there's no upward arrow, nothing here, because there's nothing that's pushing it upward. There's no rocket engine that's still on it. It's only moving upward because of inertia, and like we said in a previous video, inertia is not a force. Last one, same deal, F gravity. That's it. Maybe if you want to get picky, you can put a little tiny drag arrow. There is going to be some air resistance that goes that way, but the overall net force is down. So even though they're moving different directions, this one's in free fall, and this one's on its way up but slowing down, the net force on them and the force diagram on them is the same. There's only gravity downward. There's nothing going upward. As always, this is Mr. Stewart. Keep learning, no matter what.